here. So I will share my screen and we
Yeah,
will
ma'am.
start. Yeah, sure.
Okay, just 1 minute. Hello, Dr. Basundara.
Yeah, hello, sir. Good evening, sir.
Good evening. We have parallelly interview is going on, so I was just switching between the things. So,
Sure, sir.
hmm.
So I think my screen is visible.
Yeah, so you can make it full screen.
Yeah. So is it okay right
Yeah,
now?
fine, fine.
Yeah.
Very
Uh,
much perfect.
shall we start?
Yes. So before we start, Dr. Basundara and me, we both have done the PhD from Indian Institute of Technology, Bhubaneswar, under Professor Ganapati Panda, and she has been very active in her research at NIT Warangal and doing good in the field of applications on hearing aid design and the signal processing. So welcome, Dr. Basundara, to this platform, and we'll have an interesting session from you.
Thank you, sir. Thank you so much. Yeah, I'm highly obliged by your invitation and I'm highly thankful to you for having me over here. Okay, so we will start mostly.
Yes, please
Huh.
start.
Okay. Yeah. So once again, very good evening to all the participants. So mostly in this talk today, I will be talking about application to hearing aid design and how optimization techniques we have incorporated for enhancement of speech quality, speech intelligibility for in the context of the design for hearing assistive devices. So, just a little bit introduction. Already, a lot has been said about the optimization in this complete so many days of FDP program. So, just I will start with a little bit of introduction. That optimization is an attempt to obtain best possible result in the given specifications and conditions. So here, basically, we are concerned with finding the maximum and minimum of any function, possibly subject to constraints for continuous and differential functions. So this is the basically an optimization process flow that how we proceed for choosing any optimization technique and how we incorporate that particular optimization technique in order to solve any application or any problem in for any particular application. We start with choosing a design variable, formulating constraints, formulating objective function, setting a variable limit, choosing an algorithm to solve the problem, and solving the problem to obtain desired result. So, classification of optimization techniques, there are various traditional conventional classical approach like linear programming, non-linear programming, integer programming, as well as with the gradual advancement in the techniques, heuristic approaches have also come into picture, which incorporates bio-inspired techniques, swarm-based intelligence, neural network, fuzzy logic, likewise. And we can have single as well as multi-objective optimization also, depending upon the order of the optimization that we are taking into consideration. So most basically in this particular session on the talk, I will be mostly focusing on the optimization techniques which we have been working on and we have incorporated for the design of hearing assistive devices. So optimization techniques for hearing assistance. So let's start. Mostly, just let me set the background with a little bit of introduction as I talk about hearing assistive devices and why do we use it, why do we need it, and in what context does there is the need of use of this particular device, and then we will slowly move on that how we are incorporating all these techniques, optimization techniques. Mostly, I will be talking about how neural networks based and architectures and which optimization we have been incorporating to train the model for probably solving some of the signal processing problems in the design of the hearing assistive devices. So, just a little bit of general introduction that hearing is a very vital part of our day to day life. It is one of our primary sense organ, which is intricate, fragile, yet very precious. It is as dispensable as the sense of sight. So, mostly 360 million people, among which 328 million adult and 32 million children, they are found to suffer from hearing loss. And it is more likely that most of the population above 65 years of age, they are more likely to suffer from this. So if we look from a deeper perspective, we will understand that consequences of hearing loss, it is not just physiological or psychological. Rather than it is very much deep rooted in all the dimensions of the life, be it isolation, loneliness, depression, frustration, and so on. The list is long enough. Here, I would like to quote one very appropriate quotations from Helen Keller that blindness separates us from things, but deafness separates us from people. So it has been observed that hearing loss, though if we see it looks like just as a physiological limitation, but it is very much deep rooted and it has shown its impact in various other dimensions of the health of the particular person who is suffering from this, like dementia, cardiovascular vascular diseases, hypertension, smoking, and so on. So, with regard to this, there are many challenges still existing in the society. There are still people which are very much reluctant, and it has been found out that as less as 1 in 10 and 4 in 10 persons suffering from mild and moderate to severe hearing loss, they prefer to use these hearing assistive devices. So, lack of awareness, affordability, and some of the stigma related to it, they are some of the major factors which inhibit them from seeking some of the help. So, recent advancements in the field of signal processing techniques, they can be utilized to enhance the sound quality perception, speech intelligibility, and listening comfort of the users. It can impact the lives of millions of people globally by improving their hearing related facilities. So, as I talk about hearing aid or how we can apply the recent advancement in optimization and signal processing technique for enhancing the quality of hearing assistive device, basically I would like to start with a simple um, explanation of a hearing aid. So, hearing aid is an electronic battery operated device that processes and changes sound to allow for improved and enhanced communication. In a very basic form, it incorporates microphone, loudspeaker, amplifier, and a battery. So different types of hearing aids or hearing assisted devices, they are available in the market as we can see, and people use them or choose them as suggested by the audiologist or as per their aesthetic preferences. Like here we can see that we have three to four categories: behind the ear, in the canal, and completely in the canal. These are a different architectures. They all come with their own pros and cons, and of course the audiologist as well as the age and the convenience and the aesthetic preferences of the users, they choose them. Like behind the ear, it is easy to change the device, it is easy to maintain the device, change the battery compartment and everything. And similarly, on the contrary, if we look for the completely in the canal, which is completely inserted inside the canal, it is little bit of inconvenient to take out every time so as to fine tune the device as well as to change the battery. So, if I talk about signal processing applications for hearing aids, so there are many contexts in which we can apply the advancement in the techniques of signal processing as well as the incorporation of the optimization technique for enhancing the quality of the life of the users which are using these devices. If a person is using hearing assistive device, the very general expectation of the person would be to have as much as of a normal listening experiences without any of the extra effort to put in for that, to lead a life in as many as normal way. But despite using the device also, it has been observed the users are not completely satisfied with the device. There are certain obstructions as well as problems being faced by them, which leads to degradation and deterioration of the sound quality being perceived by them, like noise interferences, acoustic feedback, so on. So these are some of the challenges which are being perceived by the users, which leads to the sound degradation as well as sound quality is not up to the par what the person is expecting, which leaves them completely dissatisfied. And further, in many of the cases, it also leads to discontinuation of the usage of the device, which is not at all quite suggestible and advisable. So mostly my work is focused on, or I will be talking today's this talk about the techniques of how we have handled the problem of acoustic feedback being faced by the users. So, as I will talk further on, that acoustic feedback is a physical phenomena, inherent phenomena, which is being faced by the users of this device. And this feedback, it further leads to sound quality degradation and a persistent howling sound perceived by the users, which is quite annoying for them. So, as I will show, that this is a very general we can say that this is a ear pin and this is a very general description of acoustic feedback. So due to the compact nature of the device, and it is a body wearable device as well as it is a size and the area and power constraint device. So both the electronic components, be microphone as well as speaker, they are placed in close proximity in the device, and which further leads to an inherent acoustic feedback phenomena, which is quite challenging to completely avoid. So, as a designer, as a signal processing engineer, what our best possible way to handle this is to that we can try to mitigate its impact as much as possible. So that what I will be talking on over here. So there are certain causes of feedback like improper placement of the device in the canal or inside the pinna of the user, or there are certain malfunctioning of the device manufacturer defect in itself, or certain vents or holes are present in the device which further leads to the feedback phenomena, or the presence of handset or any closed surface near the ear of the person. So it has been observed that due to this acoustic feedback, it degrades sound quality as well as speech intelligibility. And it leads to another impact, that is occlusion effect, which is perceived as howling and which is quite annoying for the user. So in this, my most of the work which I have been working on, that has been focused on that how we can try to mitigate the impact of this acoustic feedback as much as possible, so that the listening experience of the user is enhanced in a more appropriate way, and the satisfaction level of the users can be elevated. So this is the basic general block diagram of acoustic feedback cancellation in a hearing aid. So I will try to explain it this first because this is the basic fundamental block diagram, and we will be using this further in the different techniques which I will talk on. So here we can see that this is the input desired signal which is supposed to be captured by the microphone of the device. Now here we can see, or I will try to um, uh, explain this in a part by part manner, such as first we will try to see what is this one. This is known as the forward path of the device. So this basically shows the signal flow diagram of the forward path of a hearing assistive device, where there is a microphone to capture the incoming desired signal, which is supposed to be enhanced and delivered to the tympanic membrane of the user. And there is a forward path. So this forward path, this basically consists of an amplification as well as different filter banks are there. Filter bank is there. There are different filters so as to enhance the quality of different frequency band of the audio signal that we are having over here. Now, again, there will be a speaker or a loudspeaker whose task will be to deliver the processed sound to the tympanic membrane of the user. Now, due to the close placement of the microphone over here, as well as speaker, and as we have seen previously, means they are completely in a case in a small, means like in a small case, this all things they are completely encased. So there is a quite good probable chance that the processed sound which is supposed to be delivered from the loudspeaker to the tympanic membrane of the user is again picked up by the microphone, and then this gets mixed up with the incoming desired signal. And in the next round of the iteration of the processing, this mixture is again going for the forward path processing of the complete audio signal. So what happens over here? This here we can see that this green one, light green portion, this shows the phenomena of acoustic feedback. This shows the transfer function. This is the transfer function showing the characteristic of the physical acoustic feedback path which has been obtained in the laboratory setup. So here we can see that this microphone, it is not able to differentiate between the incoming desired signal as well as the feedback signal. It captures both of them. And then this mixture of the signal, this combined signal, is being further processed towards the forward path of this hearing assistive device. Now this complete process goes on again and again, iteration after iteration. And one major point I would like to highlight over here is that this phenomena moves this complete system into a closed loop phenomena. So this is one of the major problematic part over here, is that this acoustic feedback, this moves this complete system towards a closed loop system. And there is a good amount of chance for moving the system towards unstable condition due to this feedback phenomena. So what we are trying to do over here, that we are trying to design an acoustic feedback canceller over here, which we can incorporate in the backward path of this complete device. So here you can see that in the forward path, the general working or the normal working of the hearing assistance or the hearing assistive device is supposed to be happening. In the backward path, this acoustic feedback is happening. So acoustic feedback canceller that we are supposed to design, we will be designing and appending it again in the backward path of the this complete device or this complete setup. So here, basically we are trying to use an adaptive model so as to design an acoustic feedback canceller. So if we want to look, we can look this problem from the perspective of system identification also. That we are trying to identify this acoustic feedback path with the help of an adaptive model. But there are some of the prime differences between this and system identification. That first of all, whatever the estimation error will be generated over here, that will be just not simply the residual of the feedback and the anti-feedback signal. Here, ideally, whatever the estimation error we will be getting, if an ideal condition is happening, that we are trying to completely mitigate the impact of this acoustic feedback so that the feed generated, let's say this is the generated feedback signal, which is approximately equal to the original feedback signal, then the estimated error should be as good as the incoming desired signal, and this incoming desired signal should be further passed on to the forward path of the hearing assistive device for further processing. That is what this is the ideal condition that we want our model to do. But of course, since we are trying to train our model, we are using certain optimization technique to make the model learn, train so as to behave in the same way and to generate a very near and a good approximation of the feedback signal. But then also certain amount of residual feedback signal will be remaining, which will be contaminating this our incoming desired signal, and which will be further passed on for the forward path of the hearing assistive device. So this is the basic fundamental model of our acoustic feedback cancellation of hearing assistive device. Now I will show the techniques that we have incorporated so as to train this model in under certain conditions, and how of nonlinearity and outlier interferences under such real-time conditions, and how we have trained the model so as to generate a very good and accurate approximate of this estimated feedback signal so as to mitigate the impact of the feedback as much as possible. So this is the most basic fundamental block diagram, or we can say signal flow diagram, that how signal is flowing or the incoming desired signal is supposed to be enhanced in the forward path of the hearing assisted device, and how acoustic feedback is coming into picture, and how we can further design an acoustic feedback canceller to be appended so as to mitigate the impact of this acoustic feedback as much as possible. So one thing which I would like to highlight over here, that the estimation error will be near to this, or it should be as much close to as this desired signal. In addition to the residual of deviation of this generated feedback from the original feedback. So it contains two components. So that's why there is a problem of bias coming into this picture, because here the estimation error is not only the residual of this. In addition to this, we also have this incoming desired signal component over here. So therefore the estimation error is of course correlated with the desired or with the incoming signal of this adaptive model. So that's why in this application, we are using a pre-whitening filter, adaptive predictor filter, to pre-whiten the incoming input as well as the estimation error before we are feeding both of them to any adaptive algorithm for fine-tuning the model, the weights of the model. So this is one of the major changes that is happening for this particular application in comparison to a normal system identification problem, that it is a closed loop, and secondly bias is coming into picture, and we have to work towards mitigating the impact of the bias as well so as to enhance the quality of fine tuning or the adaptive learning of the model. So next I will talk about some of the work that we have done in this context. One is that we have designed a nonlinear adaptive feedback suppression technique with the incorporation of exponential function link adaptive filter, because there are very good amount of chances that because of the usage of low quality loudspeakers, the system can move into a non-linear range because of the saturation of such devices. So for this we have used a functional link adaptive filter, and where we have incorporated certain of the parameters, and we have enhanced the working of this with the usage of adaptive exponential parameter and a decorrelation factor be incorporated into this. So I will just show you the block diagram over here. So if you see, this is very much similar to the block diagram what we have seen previously. So let me compartmentalize it again for the simplification purpose. Let's see, if we say this is the forward path, again this is the feedback path. Now here this is the adaptive feedback canceller or acoustic feedback canceller designed based on the functional link adaptive filter. So basically here we have used a functional link adaptive filter that has been constructed on the conventional trigonometric functional link. Along with that, we have used an adaptive exponential parameter so as to enhance the nonlinear modeling capability of this functional link adaptive filter. So just these are the different blocks like functional expansion unit. These are the weight vectors which are being multiplied to each of the functional expansion units. This is the uh, weight update unit, and this is the adaptive parameter update unit. So here in this particular case we are using two updates. One is weight vector. This weight vectors, they are completely updated, And along with this, there is an exponential parameter. If I say there is an exponential parameter in this functional expansion unit as well, that exponential parameter is also updated. So now here we have two updates, and this two update we will be following, or we will be doing with the help of a gradient descent based optimization technique. So these are just a detailed expansion diagram of this functional expansion unit, where we can see that the input to the adaptive model, which in turn is the output of the complete hearing assistive device. That input is then passed to this conventional trigonometric expansion unit, and then they are multiplied with this adaptive exponential parameter. So this particularly we have used so as to enhance the nonlinear modeling capability of this complete nonlinear model. Along with that, it is also showing a better result when we are using dynamic signals like acoustic signals, speech, or the music signal as an input. And in our case, since we are more focused towards the usage of this model for the design of, in case of a nonlinear modeling for a acoustic feedback canceller design and for a hearing assistive device, since in that most of the input signals they will be correlated in nature, as well as there will be dynamic in nature, as we see whether it is speech or music. Therefore it has been observed that the incorporation of this adaptive exponential parameter enhances the nonlinear modeling capability of this particular nonlinear model. Further, this is the weight update unit, delayed weight update unit, that has been used over here for updating the weight vector of this complete expansion unit. Now, I will just talk about some of that. Let's skip the derivations and all that. So I will talk about, this is the weight vector. This is the derived expression for the weight vector and the adaptive exponential parameter. So I will little bit discuss that how we have, which optimization technique we have used in order to get this updated weight vector. So basically we have used the method of a steepest descent or gradient based optimization technique over here. As we can see that this is a block diagram of a transversal adaptive filter, where we have different weight vectors, and we have delayed input samples. So these delayed input samples, they are multiplied by their corresponding weight vectors, and then they are multiplied, added to get the desired output. Then we have a reference signal, which we calculate the deviation, and we generate the estimation error, which is being utilized for the weight update mechanism. So the weight update mechanism can happen according to there are various algorithms for the same. But how to do this weight update? So we have followed the gradient based optimization technique. It is a very classical and conventional optimization technique, where we try to optimize a cost function in such a way that we try to optimize the cost function in order to get the minimum value of the estimation error. So basically this complete optimization problem we look with the perspective of a minimization problem, where we try to minimize the cost function. So how the cost function is created, we can generate or we can construct the cost function based on our requirement. So mostly the most common or the primarily using cost function is the mean squared error. Is the mean squared error. We can use even higher order power or like that, but this has been observed to be giving the very convenient and to use and giving an optimum result. Now what we do, we take the gradient of this cost function, and we use this gradient of the cost function in this recursive expression of the method of steepest descent. We take the negative of the gradient, or we move in the direction opposite of the gradient of the cost function with respect to the weight vector. So ultimately, we are trying to find an optimal value of the weight vector that will give us the minimum value of this cost function or the gradient of the cost function with respect to the estimation error. So this is our basic fundamental that we have incorporated even for the design of this particular weight update expression and this particular expression for the adaptive exponential parameter also, that we have tried to minimize. We have used the method of stochastic gradient based optimization, method of steepest descent. We have constructed the cost function. Mostly the cost function that has been constructed is the mean square error only. And then we have tried to take the, if I write like this, then we have tried to take Jn. If we write like this, we have tried to take the derivative of this cost function with respect to the weight vector. And then this derivative of the cost function with respect to the weight vector has been incorporated in this expression of the method of steepest descent to obtain a recursive expression for the update of this weight vector. So that's how we have come up, or we have derived the expression for the update of the weight vector. Along with that, the update of this adaptive exponential parameter also. So there are two updates over here, or two adaptive parameters in this particular design. Okay, so this is a very means general way. Here, this is the cost function. Further, as I will show on in the slides, that further we have also moved on for the design of certain robust cost functions, where those cost functions, they are not directly dependent on the estimation error. Rather than that, we have used certain robust norms like Wilcoxon norm, as well as other designs, where so that the dependency of the exact estimation error on the cost function is reduced, so that when there are certain unclear interferences or non-Gaussian noise interferences, in that scenario this mean square error is observed to not be yielding such a good results over there. So in those scenarios, so as to enhance the performance, as to maintain the performance of the adaptive model in such scenarios of interferences, of outliers, or wear and tear at that particular time, those robust cost functions we have incorporated. And we have used the technique of a steepest descent optimization technique only, so as to derive the expression for the weight update. So these are some of the cases expressions for considering the nonlinearity. As I am talking about the nonlinear model, so mostly this acoustic feedback canceller that we have designed, that is nonlinear in nature, for handling the nonlinearity encountered at the loudspeaker or the microphone end. So in order to mimic that condition of the nonlinearity, we have used these three particular expressions, like for sigmoidal nonlinearity, clipping nonlinearity, time hyperbolic, so as to mimic those solutions. And these are some of the performance parameters. So this is the impulse response to the acoustic feedback path that has been obtained in the laboratory requirements for two particular conditions, that is one with no obstruction, one with obstruction. And these are some of the performance parameters, like we have used PSQ score, PAQ score, and a noises database that we have used for obtaining the input desired signal. So these are some of the results which I would like to show in terms of PSQ value. So PSQ basically stands for perceptual evaluation of speech quality for three different cases. So basically here three different cases, it shows different cases of the non-linearity. Like one, we are showing the non-linearity or modeling the non-linearity with one expression, like say sigmoidal non-linearity, one with soft clipping non-linearity, and this case 4 we have incorporated two non-linearity simultaneously, one at microphone and one at loudspeaker end. So this is our proposed technique, that is correlated improved adaptive exponential functioning adaptive filter. So mostly this PSQ score, it shows that how well and good the processed sound will be perceived by the user. Okay, so how it will be perceived? So it is perceptual analysis. So basically this score, it varies from 0 to 4.5, where 4.5 shows the best quality. So as we can see that in all the three different cases, our proposed technique is able to achieve enhanced value of the PSQ score as compared to other cases, other existing state-of-the-art techniques for different ranges of the SNRs of the input signal, and for different types of the noises interference also, like car noise, street noise, babble noise, so on. Similarly, this graph, this shows the plot of the added stable gain. So added stable gain, it shows the additional amount of the gain which can be made available as a result of the employment of the feedback cancellation technique in the hearing assistive devices. So here we can see that we are able to maintain a good amount of added stable gain, ranging in between to 25 to 30 likewise dB for different cases of input signal being taken into consideration. Along with this graph, it shows the robustness in terms of that how our model is able or robust towards handling the changing in the intensity of the nonlinearity. So all different cases of the nonlinearity that we have seen, so we just vary the intensity of the nonlinearity by changing the threshold parameter or the saturation grade parameter, and by changing this threshold parameters or certain constants, the degree of non-linearity intervention it changes. And what is the response? What is the response of our desired model towards this changing non-linearity that we have tried to study and investigate through these plots? Similarly, another thing which I would like to show you that this is one um, structure that has been designed by us for effective or for efficient area and power consumption that we have taken into consideration. So this is basically we have done up to an structure or architectural level design. So I will show you here that how with the usage of one folding concept we have tried to or we have tried to how much manage we have managed the computations as well as the power and the resource area for this design of acoustic feedback canceller for hearing assistive devices. So this is one structure which I am showing over here. This is a proposed full parallel structure with the help of partition time block LMS algorithm we have used for hearing aids. So this is just in the form of different parts and different blocks. The architectures has been shown over here. So here we have different arithmetic units. So this different arithmetic unit, they show the internal mechanism of the working of the acoustic feedback canceller. Like first, if I talk about register array, so this shows that how the input samples or the input vector will be rearranged so as to get, as I talk about here, we have used partitioning idea over here, that the complete impulse response we have partitioned into different blocks. So basically partitioning we have done so as to rearrange this complete architecture into a more modular way that will help in the in a better way of designing. So therefore here, as we can see that the input samples here, there are a lot number of registers. Likewise here they are arranged in such a way that whatever the input samples or the vector will be coming, that will be further partitioning into different input matrices. Now we have different arithmetic units. Like this arithmetic unit is entrusted with the task of doing convolution pertaining to the generation of the output of the filter. This arithmetic unit is entrusted with the task of doing the correlation for generating the intermediate result, which will be further helpful for the weight update unit. So just I will show that how by incorporating an idea corresponding to folding of these two arithmetic unit, we have tried to save the area and the power consumption in this complete design for the acoustic feedback canceller. Like if I will just show that internal structure of this arithmetic unit 1 and arithmetic unit 3. So as I talk about both in the filtering process, let me show you. First we will be generating, these are the basic steps. First we will be generating the output of the filter or the adaptive model. Then we have to find out the estimation error, and third our job would be to do the update of the weight vector. Now this is a sequential process, and while we were designing this full parallel structure, we observed that this arithmetic unit 1 and arithmetic unit 2, they are doing two similar operations of convolution and correlation, and they have a very similar internal structure which I will show over here. So this is the internal structure of arithmetic unit 1, and this is for the arithmetic unit 3. This is for AU1 and this is for AU3. Both of them have internal matrix vector multiplication unit, which is further coming as an inner product cell. And as if we observe that both of them share the same inputs as well. One of the input is same. Only the second input is different for both of them. Here the in the AU1, one input is the weight vector, which gives output of the adaptive filter. And in AU3, the another input is the error sample or the error vector, which generate an intermediate value which is utilized further for the weight update process. So while designing this, we have observed that each of them, they remain idle for half of the clock cycle and they remain working mode in for one half of the clock cycle only. So this particular thing further or this observation we have further incorporated so as to design a folded structure where both the units AU1 and AU2 they are made to work from the same unit arithmetic unit by using a multiplexer and a demultiplexer. So this is a folded structure over here where you can see that this folded structure, of course, the internal working, internal mechanism, internal component remains the same. Only thing is there here that in here processing element, we are using, this is the internal diagram of the processing element. We are using one multiplexer and a one demultiplexer over here, so that during the one half of the clock cycle when we are interested or when we need the output of the adaptive filter, this multiplexer will facilitate the usage or the incorporation of this adaptive filter to this particular arithmetic unit, so that this arithmetic unit will function as arithmetic unit 1 and it will give as its output the output of the adaptive filter. Now, in the second half of the clock cycle, when the output of this adaptive filter has been already generated, then we have utilized it to get the estimation error. For the next half of the clock cycle, this multiplexer will facilitate the incorporation of this estimation error into this module. And by virtue of that, then this module will be working as arithmetic unit 3. And it will be generating the intermediate value which will be further utilized to the weight update vector. So because of the similarity of the internal structure of these two units, we have folded them. They are working in one particular unit so as to optimize the space and the area and the power consumption. So these two structures we have proposed and we have observed. So here you can see that in the comparison of the synthesis result, that for these two structures, if we look forward, we have been able to at least marginalize the power consumption as well as the area consumption for the proposed structure. And of course, as compared to the existing state-of-the-art algorithms, there is an improvement. But from the full parallel towards we go towards folded also, we have marginalized the area and the power consumption as well. And this plot also shows the comparison of area delay product and energy per sample consumption. Also, we have been able to reduce with the incorporation of the full parallel as well as folded architecture for the acoustic feedback canceller design as compared to the existing techniques. Now, another work which I would like to talk about here is design of the robust technique. So, in the first work which I talked about, that how we are designing this acoustic feedback canceller. So, mostly these are adaptive models, and when we go for the design of these adaptive models, we are very much focusing on the designing of the cost function, because based on the cost function only our adaptive models will be designed. So whatever we want or whatever quality we want to impart to our adaptive model, that we are taking care while designing our cost function only. So as I told, or as I've discussed previously, that the primarily used cost function is the mean square error, but it has been observed that in the case of outlier interferences, impulsive noise interferences, as well as due to the certain breakdown of this microphone analog to digital converters, this electronic components or non-Gaussian noise interferences, this mean square error is not yielding satisfactory result. So in that case, we move to another way of designing the cost function. So in one of our work, we have used a more robust norm, as I would like to say, Wilcoxon norm, that we have taken into consideration for the design of the cost function. So previously, when we were talking about the design of the cost function, we were using the mean square error. Now, instead of using this MSC or the mean square error, here you can see that if there is an outlier interferences or impulsive noise interference or non-Gaussian noise is there in the background, then that will be quite reflected in the estimation error that is being generated. Now, if the cost function is constructed directly upon the estimation error, by taking into consideration the estimation error, then it is quite difficult to not not expect that our adaptive model will not be impacted by that particular interference. So in order to handle that particular situation, here we have taken into consideration, you can see, we have taken into consideration one score factor associated with the estimation error rather than directly taking the estimation error, or basing our complete design of the cost function on the estimation error. We have used one score factor constructed by the rank of the estimation error. So basically, this is a block-based implementation where a block of error samples will be created. So let's say if the length of the block is, let's say, size is 5. So we are creating total 5 number of error samples. Now these error samples, they will be arranged, sorted, and and we will be imparting them rank. Now, this rank factor will be further utilized to calculate the score associated with each of these error samples. Now, this score associated, this will be utilized for the construction of cost function. So this is just the mathematical expression that how we are calculating the rank and how we are calculating the score. Now, same the method of steepest descent that we are utilizing over here, the optimization technique, so as to get the optimal or the updated value of this weight vector. Only thing is that we have taken into consideration is that how we will design the cost function. So the robustness or the quality of that the robustness for adaptive filter, that particular quality we are imparting here only while designing the cost function. So these are all the derivations. So this is the final updated weight vector according to this proportionate normalized Wilcoxon LMS. So as I will say, we have used a proportionate factor over here so that we can impart more adaptation energy to the active coefficients. So it has been also observed or seen that the impulse response or transfer function of the acoustic feedback, it shows sparse nature, that all of the coefficients, they are not directly active in nature. There are some redundant coefficients as well. So not giving, we are imparting more adaptation energy to those coefficients which are active in nature so as to enhance the convergence process. So basically here we have used one convex uh, optimization process or convex optimization technique by which two this is a hybrid method where two adaptive filters, I will show the block diagram so it will be more clear. So like here we have used, so this adaptive filter is being trained by proportionate normalized Wilcoxon LMS algorithm, and this second one by Wilcoxon LMS algorithm. So by use of convex optimization or convex way of merging, we have tried to incorporate the benefit of both the optimize of both this adaptive filter while designing this hybrid model. Because with the incorporation of this proportionate normalization over here, the convergence factors enhanced to a greater extent. And with the incorporation of this Wilcoxon norm over here, the steady state performance is increased. So if we want to get a fine tune or a greater extent of balance between both convergence steady state performance in terms of misalignment, so we have tried to use a convex optimization so as to merge the benefit of both the adaptive filters in this particular context. So here two cost functions are there in correspondence to both the adaptive filters, and we have used the a method of steepest descent based optimization technique so as to optimize this cost function to get the final weight update equation corresponding to these two adaptive filters over here. So I will show you some of the plots for this. So these are some of the parameters that we have incorporated. Basically, we have used different noises speech segments from timid database, from noises database. So these are basically mostly the database that we have taken into consideration. Along with that, the performance parameter, which we have utilized, which is shown over here, is added stable gain. That is the additional amount of stable gain which can be made available as a result of the employment of the feedback canceller. So if it is visible from here, we can see that this light gray line, as we can see, this is able to merge the benefit of
Dr. Vasundhara, sorry to interrupt you, but your voice is not coming. Can you hear me, Dr. Vasundhara? Hello, ma'am. Sorry to interrupt. Your voice is not coming. Can you hear me, ma'am? Ma'am, voice is not coming.
Hello, Dr. Basundhara. Can you able to listen? Hello, Dr. Vasundhara, can you able to listen? Dr. Vasundhara, can you able to listen? मैं दोनों से ही बोल रहा हूँ. Dr. Vasundhara, can you able to listen? Hello, Dr. Vasundhara, आपका no, no.